Welcome to Talkcast, and for audio-only listeners, this is episode 202 of the podcast, and I'm back for 2024 and a new year of episodes. Many have been in the works for some time, and so fans may be wondering, why so long between episodes recently? Where have you been, Brett? Well, the main reason is other projects. If you're following me on social media more broadly, you will see that I've been producing a bunch of content, especially with Naval Ravikant over there on AirChat in particular. And of course, we've been producing the Deutsch Files, a conversation that occurred over a number of days late last year between myself, Naval, and David Deutsch. We travelled over there to Oxford to have a discussion with David, and we now have 3 episodes, the Deutsch Files 1, Deutsch Files 2, and Deutsch Files 3, which were first published, and it's always first on AirChat, and then eventually it's produced and edited in a more refined way by the wonderful Arjun Kamani, who produces a great transcript for us. The incomparable Arjun Kamani, who puts together all of the episodes into a form that we can then export to all the different platforms. So they're out there right now. If you haven't heard them, go to the Naval podcast. Perhaps the best place to go is here to Naval's website and to sign up here. Subscribe to his newsletter where you will get the transcript, the hyperlinked transcript, and the audio of the episodes that we've done with David, as well as Naval's entire back catalogue as well of episodes that he's done with me and with other very interesting people that he's talked to over the years about business. He's talked with his colleague Nivi. He's talked about spirituality with various people. So the Naval podcast, well worth signing up to get all the stuff that Naval is interested in particular, recently the stuff to do with David Deutsch and the Deutsch Files, which are brand new, our effort to spread the ideas of David Deutsch and that worldview that comes out of the beginning of infinity and the fabric of reality more broadly. But AirChat is where I've been putting a lot of effort over the last few months, which is why I haven't been quite so active here on Talkcast. But don't worry, we're coming back to Talkcast again now for 2024. AirChat is a wonderful place to go if you want intellectual discussion. It's a place for something beyond regular social media. It's both a podcast production house and a conversation facilitator all in one. Really a very new kind of app that's different to things like Clubhouse or Twitter Spaces that you might think that it's similar to. No, it gives the user a lot more control over their channels, so to speak. And over there, we've also got channels devoted to discussing the Deutsch Files. So come and talk to Naval and myself and Arjun all about the Deutsch Files and what we're working on there. What we've talked about, the content of the work of David Deutsch. It's a place that sort of centralizes, it's a nice hub for discussions about the work of David Deutsch with like-minded people. I should add, I'm also planning on doing some more live streams over the coming months as well, but AirChat's a great place for me to interact with Talkcast fans and others on AirChat as well. So come and talk to me there. Come and sign up to AirChat at www.getairchat.com. And we can talk about, well, all the stuff that I talk about here. But Talkcast isn't going anywhere. It's not changing. It's just a little bit slow to get started this year, that's all. But over the years that Talkcast has been running, people will notice that there have been times, especially early on, where, I went months without producing an episode. So now and again that happens where I just have to read and research and, look more widely into what might be coming up for this year, this intellectual year, in terms of what's going on in the intellectual zeitgeist out there and what I might want to focus on. So it's a whole bunch of ideas there bubbling away in terms of what episodes I'm going to produce over the coming months. One thing that might change just a little is I'm going to be doing some more interviews than what I normally would. I've talked to David on this channel before. I've talked to Kiara on this channel before. I'm not planning on turning Talkcast into an interview show. That's not what Talkcast is about primarily, but I do want to talk to some other physicists who have worked with David Deutsch, for example, among other people, but in particular those who have been influenced by the work of David Deutsch and might be taking it into other directions, and those physicists who might be Popperian in their let's say, intellectual outlook and to see how critical rationalism might affect the way in which they look at the world and the way in which they do research, let's say. So look forward to that over the coming months, in addition to these regular episodes. And today, as you will notice from the title, this is indeed a regular episode. Modulo this extended introduction, because it's the first one of the year. But here we do find ourselves at part 3. I think there's going to have to be a part 4, but this is part 3 of chapter 10, The Nature of Mathematics from the Fabric of Reality. Today we're going to get to, finally, the nature of proof and Gödel, Penrose. We won't quite get to, I don't think, my favourite line in all of the Fabric of Reality, the one that I have quoted so often throughout these podcasts, on Twitter, on any social media outlet that I have. There is one line, and I think fans of TOCcast will know what that line is, with respect to the subject matter of mathematics and the conjectural nature of mathematics, the difference between the subject matter and what we know of the subject matter of mathematics. We won't quite get to that line today. We'll have to save that until part 4. But we are going to begin today, eventually, once I get through this extended introduction, with a reference to the work of David Hilbert, one of the great mathematicians of the 20th century, who devised a program known, funnily enough, as the Hilbert program to this day, where he sought to secure the entirety of mathematics on firm foundations. In other words, just to have a single, final, finite set of axioms from which anything in mathematics could be proven. This would turn mathematics as a whole into nothing but a calculation exercise. All of mathematics, whatever your question, could be derived from these final, complete set of axioms. After all, why not? If it worked in geometry, where you've got a single set of axioms, as Euclid did, and then you were able to prove everything that followed for, Euclidean geometry, or it works in, say, set theory, where you begin with a set of axioms and you prove all the stuff that you need to know in set theory, or calculus, you begin with a set of axioms and you can prove everything that you can within calculus. And each of those different branches have their own set of axioms. Why not just bundle up all of the axioms together and just, no matter what the disparate domain of mathematics, you have this one big list of axioms, and from there you can just prove everything that follows in mathematics. Russell and Whitehead even wrote a book, the Principia Mathematica, which set out to formalize all of mathematics in kind of like the way that Hilbert suggested. Principia Mathematica, this huge multi-volume tome, was intended to, in a sense, reduce mathematics to basic logical foundations. This, among other things, is why I've personally always gravitated towards logic myself in matters of mathematics. Philosophical logic, mathematical logic, they're subtly different kinds of logic, were the most interesting branches of mathematics for me at university. Like, as a physics student, like all physics students, you have to take just so much calculus and so much linear algebra that, for me, doing logic, doing formal symbolic logic was like a bit of a holiday. It gave you a chance to get away from the hardcore linear algebra stuff, the hardcore multivariate calculus stuff, and to go into something that didn't really have a whole lot to do with physics and chemistry and science type stuff. It was just completely abstract as you could possibly want it to be, formal logic. It was fun because it was a way of just solving puzzles. If you've never done proofs in symbolic logic, I can recommend it. It's kind of like a crossword puzzle, or, very similar to certain kinds of algebra that you might do at school. It is a kind of algebra, actually. Anyways, I know people who don't like mathematics because they've had bad experiences at school or whatnot, won't know what I'm talking about, that mathematics can be fun, but it actually can be, especially logic. With logic, I never thought that I was solving some deep mysteries. I was never under any illusion that I was even improving my own thinking more broadly, for what it's worth, even though that's the way that universities often would sell things like a degree in philosophy or even a degree in science for that matter, but especially, do logic, do our subject in logic because it will help with your ability to think clearly. I never bought that. And as I did the subject, I thought, no, that's a lie. That's a marketing strategy. It doesn't help you with your thinking, broadly speaking. It was, at best, puzzle solving, and I found it fun. Some people have a strangely high opinion of those with skill in mathematics or even skill in formal logic, let's say, because they're under the misconception that somehow or other it generalizes, that these skills in mathematics or skills in logic are generalizable. In other words, they help you to think better in science, philosophy, or just thinking more broadly. But it isn't. Knowing formal logic barely ever helped me to identify logical problems in explanations or arguments more broadly. That was a different skill. Even though they would tell you in logic class, like, here, this can help you to understand problems in legal arguments or problems in scientific arguments. I never had occasion to actually apply the logical rules of inference that we were taught and that you get taught in logic class to anything beyond what was going on in logic class. It just didn't work that way. I mean, okay, so maybe there were some very, very rare occasions where in philosophy, you're reading a philosophical argument and you go, aha, there's an example of assuming the consequent or something like that. There's a certain logical fallacies which you could perhaps identify. But that didn't really come from formal logic. These were informal fallacies, as they're called. Different thing again. Certainly, being proficient in calculus, as any physics student generally becomes, certainly never helped me become a better thinker. In fact, being good at calculus doesn't make one better at physics and chemistry, for example. But people do have that misconception. The misconception that mathematics equals intelligence in some way. It just doesn't. It's its own skill. It's like being good at languages or music or any other intellectual endeavour. I'll put in a word for perhaps Popperian epistemology here. I do think that sometimes epistemology of that kind can help. It can be a way of generalizing your capacity to think more critically about stuff. But even then, not always. There are some people reasonably proficient, I would say, in Popperian epistemology, who I find have huge gaps in their knowledge of things that I think should just be common sense background knowledge. Or they reach bizarre conclusions in morality and history despite understanding the nature of conjectural knowledge. At least at first pass they do. Some brilliant mathematicians I've seen out there are held hostage by the pattern, as David Deutsch calls it, which suggests poor critical thinking skills. Others are devotees of Bayesianism. So, go figure. People can be brilliant mathematicians or brilliant physicists, yet be mired in terrible misconceptions. These skills can, in some sense, be partitioned inside of people's minds. They just aren't generalizable. You can be really good at one thing and yet completely terrible at thinking more broadly. Mathematics, like logic, like learning a foreign language, ultimately is rather like coding. There are some rules to learn, then once you understand some of the basics, you can put them together in new, interesting, and even creative ways. But knowing any of those things isn't really generalizable, as I keep on saying. You don't get any special insight into science more broadly, or philosophy, or history, or even critical thinking because you know how to do calculus, or logic, or learn Mandarin, or you know how to code in Python. They're each their own special domain. They're each their own specialized area of expertise, of knowledge. But mathematics is placed on a pedestal. It's a peculiar subject because of culture, in particular the culture of schooling. I'm thinking about the hierarchy of subjects that you're taught at school in particular. It's just assumed that mathematics is the hardest subject. And so the smartest people do mathematics and do well at mathematics. So we're taught. And so everyone ends up coming away from school, almost everyone, even the people who do well at mathematics, not liking it because it's so competitive and only some people are good at it, and people who aren't good at it or who don't take an interest in it are denigrated as being not good students, while those who do well at mathematics are lauded as being brilliant and will go on to do great things intellectually. Now, certainly when I was at school and even at university, I wasn't immune to any of that. I was always most impressed by those who were better at mathematics than me. And even though I was reasonable at it, but I was never the best, I just went and studied a lot of it at university, but only enough to realise, I did, as I say, what I was required to do, having taken on a degree in physics. So you do a major in mathematics, the equivalent of a major in mathematics if you do a physics degree. And then I took on a whole bunch of stuff that I just found interesting, like I say, in particular, I did stuff on complexity theory or chaos theory, and of course, stuff to do with logic, formal logic. But in doing all of that mathematics, it was enough to just teach me I would never be a real mathematician. I knew enough to eventually go on to teach it at high school and even to teach first year undergraduate mathematics to teaching students. But in the end, I knew more about mathematics than I actually knew how to do mathematics, so to speak, if you take my meaning. It's kind of like a sports commentator knows a lot about different sports and can comment on different sports without necessarily knowing how to play any of them particularly well. And that's my relationship with mathematics, really. I'm a good commentator on mathematics without actually knowing how to do a whole bunch of it particularly well or to any great depth. So it really spoke to me one time, the first time I heard David Deutsch say something like, he wasn't particularly good at mathematics, which was astonishing to me at first, but then I realized I had this aha moment. I went, yeah, that's kind of the way I feel as well. I mean, David Deutsch is a guy who did part 3 of the mathematical tripos at Cambridge University. If you don't know what that is, look it up. I mean, it's the cream of the mathematics crop as far as learning mathematics goes. So David has a proper high-level degree in mathematics, and he's obviously a theoretical physicist, but he says that he's not much good at it. And I mean, I'm nowhere near that league. I'm not at his level. I have the equivalent of an undergraduate major in mathematics, as I say, and I did a postgraduate diploma in pure mathematics as well. But I know my limitations. I see enough just to know I'm not that good. So I get where David is coming from when he says he's not particularly good at it as well. Actual mathematicians who work on it all day, every day, well, they're the real deal. And mathematics, more than any other subject perhaps, I used to tell my own students, was rather like, water in a bowl. If you didn't top it up regularly, it just evaporated away, and fast. I think lots of people know that feeling. Once the exam is done and over at the end of school or university, you basically just forget almost all of it. And within, short order, within a few months, which kind of means you were never deeply interested in the subject. It was usually just a means to an end rather than an end in itself, as it is for actual mathematicians. And then, of course, within mathematicians, there's a hierarchy, just as there is in any domain, like rankings for tennis players, say. But not exactly like with tennis players, because with tennis players, you're comparing like with like when it comes to the rankings. But in mathematics, they're not all doing the same mathematics. So, the expert in calculus is not the same as the expert in set theory or logic, or, some are better at number theory versus geometry, topology, or group theory, or combinatorics, and so on. I mean, you do get the occasional unicorn type person like Terence Tao, Fields Medal winner, also Australian for what it's worth, who seems to easily traverse multiple areas of mathematics, but those kind of people are rare. Okay, I'm digressing quite a lot. Let's get to the readings. As I say, we're going to talk about the foundations of mathematics today and the attempt to reduce mathematics by people like David Hilbert, or at least the hope of people like the great David Hilbert, the attempt to reduce all of mathematics to logic or a set of axioms. Now, this is foundationalism of a kind, and David writes about this. Quote, we're up to page 228 for what it's worth. So, by about 1900, there was a crisis at the foundations of mathematics, namely that there were no foundations. But what had become of the laws of pure logic? Were they not supposed to resolve all disputes within the realm of mathematics? The embarrassing fact was that the laws of pure logic were, in effect, what the disputes in mathematics were now about. Aristotle had been the first to codify such laws in the 4th century BC, and so founded what is today called proof theory. He assumed that a proof must consist of a sequence of statements, starting with some premises and definitions and ending with the desired conclusion. For a sequence of statements to be a valid proof, each statement, apart from the premises at the beginning, had to follow from previous ones according to a fixed set of patterns called syllogisms. A typical syllogism was, all men are mortal, Socrates is a man, therefore Socrates is mortal. In other words, this rule said that if a statement of the form, all A's have property B, as in all men are mortal, appears in a proof, and another statement of the form, the individual X is A, as in Socrates is a man, also appears, then the statement X has property B, Socrates is mortal, may validly appear later in the proof, and in particular, it is a valid conclusion. The syllogisms expressed what we would call rules of inference, that is, rules defining the steps that are permitted in proofs, such that the truth of the premises is transmitted to the conclusions. By the same token, they are rules that can be applied to determine whether a purported proof is valid or not. End quote. Now, a curious thing to do with that particular example, which is often cited as an Aristotelian syllogism, is that is not the kind of syllogism that Aristotle himself usually referred to. You can look this up, but basically, although Aristotle was very fond of syllogisms, that particular example, that all men are mortal, Socrates is a man, therefore Socrates is mortal, is not one of the syllogisms that Aristotle actually used. Although he would frame his syllogisms in terms of all S are P or something like that, or no S are P or some S are P and some S are not P, in the second line of that particular syllogism that David cited there, Socrates is a man, that doesn't actually fit the form that Aristotle actually tended to use. Anyway, this is just a technical matter of logic and I'm being pedantic. What David cites there is absolutely a syllogism of a kind. It's just not a syllogism in Aristotle's sense. He would talk about all, some, and none. Look up syllogism and look up the word Barbara. Yeah, the woman's name Barbara, and Celerant. And there are 256 different kinds of Aristotelian syllogisms, but none of them actually include the most commonly cited one. Specifically because of that second line. The second line doesn't use the term all or some or no. Anyway, that's by the by. Let's keep on going. David writes, quote, Aristotle had declared that all valid proofs could be expressed in syllogistic form, but he had not proved this. And the problem for proof theory was that very few modern mathematical proofs were expressed purely as a sequence of syllogisms, nor could any of them be recast in that form, even in principle. Yet most mathematicians could not bring themselves to stick to the letter of the Aristotelian law, since some of the new proofs seemed just as self-evidently valid as Aristotelian reasoning. Mathematics had moved on. New tools such as symbolic logic and set theory allowed mathematicians to relate mathematical structures to one another in new ways. This had created new self-evident truths that were independent of the classical rules of inference. So those classical rules were self-evidently inadequate. But which of the new methods of proof were genuinely infallible? How were the rules of inference to be modified so they would have the completeness that Aristotle had mistakenly claimed? End quote. So here we have the root cause problem with assuming that mathematics provides us with absolute certainty. First, we've got the issue of how do we know that the axioms themselves that you're beginning with are self-evidently true? There's no proof that they are. You just have to assume that they're self-evidently true. And then the rules of inference themselves, they're self-evidently true. So you've got all these self-evidently true things coming together in order to provide the self-evidently true conclusion that you get. But none of it's self-evident, none of it's self-evidently true, that's for sure. Even if you think that you've got something that cannot possibly be doubted, well, as I like to say, that could just be your lack of imagination. You haven't figured out a way in which you can find a flaw with this. But just because you can't find a flaw with, the law of identity or whatever it happens to be, that through any 2 points a single unique straight line can be drawn, well, that could just be your lack of imagination. Now, I've talked about this before on the Naval podcast about how people thought that it was impossible for through any 2 points a unique straight line could be drawn. Could be false, but it is false. Okay, and you just need to think more than, in more than just 2 dimensions. David goes on, quote, "Meanwhile, mathematicians were continuing to construct their abstract castles in the sky. For practical purposes, many of these constructs seemed sound enough. Some had become indispensable in science and technology, and most were connected by a beautiful and fruitful explanatory structure. Nevertheless, no one could guarantee that the entire structure, or any substantial part of it, was not founded upon a logical contradiction, which would make it literally nonsense. In 1902, Bertrand Russell proved that a scheme for defining set theory rigorously, which had just been proposed by the German logician Gottlieb Frege, was inconsistent. This did not mean that it was necessarily invalid to use sets in proofs. Indeed, very few mathematicians seriously supposed that any of the usual ways of using sets, or arithmetic, or other core areas of mathematics might be invalid. What was shocking about Russell's result was that mathematicians had believed their subject to be par excellence the means of delivering absolute certainty through the proofs of mathematical theorems. The very possibility of controversy over the validity of different methods of proof undermined the whole purpose, as it was supposed, of the subject." End quote. So if you're interested in more about that, look up Russell's paradox and the set of all sets that are not members of themselves. Sometimes called the barber paradox as well. The barber paradox is this idea of having a barber who is someone who shaves everyone and only those who do not shave themselves. Well, the question then becomes, does the barber shave himself or not? Well, it leads to a contradiction. It's in that same class of things as, I am lying right now. Well, does that mean I'm telling the truth or I'm lying? It's a self-referential kind of paradox. And this was the problem with set theory, that you could define a set which referred to itself. And this can lead to contradictions. And as David goes on to say, but I'll skip this part, this very idea that you can have contradictions within mathematics itself presented a problem for mathematicians who were worried about putting mathematics, therefore, on a firm foundation where you could eviscerate all of these potential contradictions and paradoxes within mathematics itself. David goes on to talk about intuitionism. I'm going to skip over that part. I implore you to go to the book yourself to read about intuitionism. Intuitionists are what I would regard as simply illogical. As David explains, they deny the law of the excluded middle, which says that, for example, either there are infinitely many numbers or there are not infinitely many numbers. There's no in between. It's one or the other. But they just deny that, the law of the excluded middle holds sway in these cases. I disagree. I'll pick it up where David says on this, quote, "Just as solipsism starts with the motivation of simplifying a frighteningly diverse and uncertain world, but when taken seriously turns out to be realism plus some unnecessary complications, so intuitionism ends up being one of the most counterintuitive doctrines that has ever been seriously advocated," end quote. Remember that idea of solipsism? This notion that you can hold the philosophical position that you're the only person that exists and you're dreaming reality into existence. Well, all that's saying is that your imagination is just as complex as reality, in other words, it's just realism, plus the unnecessary assumption that realism is true, but you're dreaming it into existence. So you don't need the you're dreaming it into existence extra assumption. Just go with realism. Just go with realism and no extra assumptions. It's the same as the simulation hypothesis. This idea that everything is being simulated inside of a computer. Well, why not just skip that assumption and just go for realism? Everything just really exists. No extra assumptions needed, no special computer on which everything is running as a simulation. After all, that introduces more problems than it solves. Where is this other computer? What theory of computation is it running on? Etc. Just go with realism. Stuff exists, and stuff obeys the laws of physics as we come to understand them better over time. No need for we're dreaming it into existence. No need for it's a simulation. No need for God is ensuring that everything continues to exist moment to moment. No need for any of those extra assumptions. Just realism. That's good enough. David goes on to say, quote, David Hilbert proposed a much more commonsensical, but still ultimately doomed, plan to establish once and for all the certitude of mathematical methods. Hilbert's plan was based on the idea of consistency. He hoped to lay down once and for all a complete set of modern rules of inference for mathematical proofs with certain properties. They would be finite in number. They would be straightforwardly applicable, so that determining whether any purported proof satisfied them or not would be an uncontroversial exercise. Preferably, the rules would be intuitively self-evident, but that was not an overriding consideration for the pragmatic Hilbert. He would be satisfied if the rules corresponded only moderately well to intuition, provided that he could be sure that they were self-consistent. That is, if the rules designated a given proof as valid, he wanted to be sure that they could never designate any proof with the opposite conclusion as valid. How could he be sure of such a thing? This time, consistency would have to be proved using a method of proof which itself adhered to the same rules of inference. Then Hilbert hoped that Aristotelian completeness and certainty would be restored, and that every true mathematical statement would, in principle, be provable under the rules, and that no false statement would be. In 1900, to mark the turn of the century, Hilbert published a list of problems that he hoped mathematicians might be able to solve during the course of the 20th century. The 10th problem was to find a set of rules of inference with the above properties, and, by their own standards, to prove them consistent. End quote. So there's Hilbert's 10th problem. There's also Hilbert's second problem. Hilbert's second problem was to prove that the axioms of arithmetic are self-consistent. Now, in both cases, we've got the result of Gödel to come, and David talks about this in the next paragraph. And David says, quote, Hilbert was to be definitively disappointed. 31 years later, Kurt Gödel revolutionized proof theory with a root and branch refutation from which the mathematical and philosophical worlds are still reeling. He proved that Hilbert's 10th problem is insoluble. Gödel proved first that any set of rules of inference that is capable of correctly validating even the proofs of ordinary arithmetic could never validate a proof of its own consistency. Therefore, there is no hope of finding the provably consistent set of rules that Hilbert envisaged. Second, Gödel proved that if a set of rules of inference in some, sufficiently rich, branch of mathematics is consistent, whether provably so or not, then within that branch of mathematics there must exist valid methods of proof that those rules fail to designate as valid. This is called Gödel's incompleteness theorem. To prove his theorems, Gödel used a remarkable extension of the Cantor diagonal argument that I mentioned in chapter 6. He began by considering any consistent set of rules of inference. Then he showed how to construct a proposition which could neither be proved nor disproved under those rules. Then he proved that that proposition would be true. End quote. So here we have the genius of Kurt Gödel. Gödel showed that if you have, as David says there, a sufficiently rich axiomatic system, such as is required in order to produce, let's say, the rules of arithmetic, the natural numbers, counting numbers and adding and subtracting and all that sort of stuff, then you have a system which can be sound, that if something is sound, then it means that if you can prove something then assuming that the axioms are true, then what you get as a conclusion is also going to be true. Okay? On the assumption that the axioms are true, the conclusion is true. That's sound. Complete means that if you have something that's true, then there will be a proof of that thing. What Gödel showed was that for a system like arithmetic, using Peano's axioms, which can be used to define how you get arithmetic, how you get a system like arithmetic, then you can write down something that's true, a valid statement within arithmetic, but there may not be a proof for that thing. This was a real turn up for the books, that there are things that can be written down that are either true or false, but you can never prove them as being true or false. Now, not all axiomatic systems are like this. For example, first-order logic or predicate logic or baby logic. All of these systems, in fact, Gödel in his PhD thesis showed that first-order logic was both sound and complete. And propositional logic is, if you go through a philosophy degree or a mathematics degree, then you might have to, as an exercise, I certainly had to do this, prove the soundness and completeness of propositional logic. It's a fairly easy exercise to go through. But it took the genius of Gödel to show that for arithmetic, using Peano's axioms of arithmetic, that you can actually have a system where, and this is the overwhelming majority of systems, by the way, of axiomatic systems, that they're incomplete. That, in other words, there will be statements that can be written down which are valid statements within that system, but there is no proof as to whether or not those statements are true or false. You won't know. They're undecidable. Okay, skipping a substantial amount, and I'll move to where David says, quote, "Thanks to Gödel, we know there will never be a fixed method of determining whether a mathematical proposition is true, any more than there is a fixed way of determining whether a scientific theory is true. Nor will there ever be a fixed way of generating new mathematical knowledge. Therefore, progress in mathematics will always depend upon the exercise of creativity. It will always be possible and necessary for mathematicians to invent new types of proof. They will validate them by new arguments and by new modes of explanation, depending on their ever-improving understanding of the abstract entities involved. Gödel's own theorems were a case in point. To prove them, he had to invent a new method of proof. I said the method was based on the diagonal argument, but Gödel extended that argument in a new way. Nothing had ever been proved in this way before. No rules of inference laid down by someone who had never seen Gödel's method could possibly have been prescient enough to designate it as valid. Yet it is self-evidently valid. Where did this self-evidentness come from? It came from Gödel's understanding of the nature of proof. Gödel's proofs are as compelling as any in mathematics, but only if one first understands the explanation that accompanies them. So explanation does, after all, play the same paramount role in pure mathematics as it does in science. Explaining and understanding the world, the physical world and the world of mathematical abstractions, is in both cases the object of the exercise. Proof and observation are merely means by which we check our explanations." End quote. Isn't that wonderful? So here we have the centrality of explanation here in the Fabric of Reality, presaging, if you like, what is to come in The Beginning of Infinity. David has put explanation there as the central purpose of mathematics. It's not proof. Proof is just a means by which you can help understand what's going on in mathematics, because proof itself is a creative exercise. As he says there, Gödel had to invent a new way of proving stuff about logical systems, proving stuff about the very understanding of what proof itself is and what proofs can do, especially in something like an axiomatic system. By the way, if you want to understand Gödel's proof without actually reading the entire thing, this book by Ernst Nagel is an excellent one. It goes through Gödel's proof and it talks about Gödel's numbers, and it's an excellent introduction to what exactly went on with Gödel's proof and what is unique about it. It's about how you can assign a Gödel number, is how you can assign numbers, integers, big numbers it turns out, to formulas within a proof itself. And so you have this kind of self-referential thing going on where numbers are used in order to prove stuff about numbers. It's complicated, I know. But yeah, read this book, for example, and that will help understand. I won't go into the details right now. Perhaps if you come to AirChat, maybe I can explain some more there at some point. Let me just read a little bit more because I did mention at the beginning that we'd get to Penrose. So maybe I'll end on Penrose here today, and then we'll pick it up in next episode when we talk about, in part 4, more about the link between Gödel and supposedly consciousness, as Penrose tries to make this, what I would say is a dubious link between these two disparate areas of mystery, I would say, at the heart of our understanding of the universe or reality. David goes on to say, quote, Roger Penrose has drawn a further radical and very Platonic lesson from Gödel's results. Like Plato, Penrose is fascinated by the ability of the human mind to grasp the abstract certainties of mathematics. Unlike Plato, Penrose does not believe in the supernatural and takes it for granted that the brain is part of and has access only to the natural world. So the problem is even more acute for him than it was for Plato. How can the fuzzy, unreliable physical world deliver mathematical certainties to a fuzzy, unreliable part of itself, such as a mathematician? In particular, Penrose wonders how we can possibly perceive the infallibility of new valid forms of proof, of which Gödel assures us there is an unlimited supply. Penrose is still working on a detailed answer, but he does claim that the very existence of this sort of open-ended mathematical intuition is fundamentally incompatible with the existing structure of physics, and in particular that it is incompatible with the Turing principle. His argument, in summary, runs as follows. If the Turing principle is true, then we can consider the brain, like any other object, to be a computer executing a particular program. The brain's interaction with the environment constitute the inputs and outputs of the program. Now consider a mathematician in the act of deciding whether some newly proposed type of proof is valid or not. Making such a decision is tantamount to executing a proof-validating computer program within the mathematician's brain. Such a program embodies a set of Hilbertian rules of inference, which, according to Gödel's theorem, cannot possibly be complete. Moreover, as I have said, Gödel provides a way of constructing and proving a true proposition which those rules can never recognize as proven. Therefore, the mathematician, whose mind is effectively a computer applying those rules, can never recognize the proposition as proven either. Penrose then proposes to show the proposition and Gödel's method of proving it to be true to that very mathematician. The mathematician understands the proof. It is, after all, self-evidently valid, so the mathematician can presumably see that it is valid, but that would contradict Gödel's theorem. Therefore, there must be a false assumption somewhere in the argument, and Penrose thinks that the false assumption is the Turing principle. Most computer scientists do not agree with Penrose that the Turing principle is the weakest link in his story. They would say that the mathematician in the story would indeed be unable to recognize the Gödelian proposition as proven. It may seem odd that a mathematician should suddenly become unable to comprehend a self-evident proof. But look at this proposition. David Deutsch cannot consistently judge this statement to be true. I am trying as hard as I can, but I cannot consistently judge it to be true. For if I did, I would be judging that I cannot judge it to be true and would be contradicting myself. But you can see that it is true, can't you? This shows it is at least possible for a proposition to be unfathomable to one person, yet self-evidently true to everyone else. End quote. So, that's the resolution of the paradox. If you have a statement that refers to yourself, such as Brett Hall cannot consistently judge this statement to be true, then I can't judge it to be true because it refers to me. But you can judge it to be true without a problem. So this is the difficulty that Penrose has. But that will be where I leave it today. We've talked about certainty, we've talked about methods of proof and Gödel, and we've finally gotten to Penrose and his attempt to link consciousness there and Gödel, at least his first pass attempt to do this. And Penrose has in fact written books about this. Look up this, The Emperor's New Mind, which is about, well, exactly this idea of how the mind is not a regular kind of computer. Many physicists and mathematicians have made this point over the years, trying to link Gödel's theorem to some deep mystery of consciousness, but I don't buy it. Maybe we'll talk about that next time. But until then, bye-bye.